of our speaker, Narayanan Rengaswamy. As we just discussed, he grew up in Chennai. So that is something that I did not prepare, but yes, now we know this. And he got a master's degree from Texas A&M, and then for PhD, he moved to Duke University, where he defended his thesis last year with the title Classical Coding Approaches to Quantum Applications. Is it applications? Yeah.
Yes.
Sorry. And then upon graduating, he moved to Tucson, University of Arizona, where he has been a postdoctoral associate since September 2020. His talk is, and his research is on classical quantum communications, coding theory, information theory, and related topics. And his talk is on the application of MacWilliams identities to quantum. So MacWilliams identities is something that we know well, but coherent noise in quantum is something that I'm looking forward to learn about. Narayanan, let me pass the podium to you.
Thank you so much for the kind introduction, and thanks for having me here. So let me start by sharing my screen. Okay, can everyone see my screen?
Yes.
Okay, yeah, so thanks for having me here. So this is some work that we did recently. So we did most of the work when I was still at Duke. So this is co-authored with Jingzhen Hu, Qingjong Liang, who are math PhD students, with Robert Caldeban, one of my co-advisors. And so this is the archive number of the paper. And so the main story I'm going to try and convey today is that, so there are these coherent errors in quantum computing, which I'll say briefly about shortly. And these can be quite damaging because these can scale much worse than in the size of the system compared to stochastic errors. So stochastic errors usually build up linearly because things are not correlated, but coherent errors can sort of accumulate in one direction on every qubit. And so things get worse pretty fast. This has got a lot of attention recently, and people are working on different methods to tackle these coherent errors. We'll propose one approach, and we'll see how it connects to classical MacWilliams identities. And this is kind of one of the main tricks in our bag that we use in this paper, as you'll see shortly. This work builds upon these two papers that I worked on during my PhD. So there's something called as the Clifford hierarchy of operations in quantum computing. And so we characterized sort of some part of the hierarchy using symmetric matrices over rings. And we get some formulas on that characterize the action of these operations. And so this formula is basically the starting step to get to our main result here. And then we'll use that, we use that in this paper here to characterize codes that support transversal operations. I will define transversal operations also. So building upon these two and combining with the MacWilliams identities, we'll basically get a result. And please feel free to stop me in the middle if you have questions. Happy to take questions anytime. Okay, so let me begin by talking about what I mean by coherent errors. I want to sort of directly jump into the model. So gentle coherent errors. So these are, you can think of as basically like rotations of qubits over a particular axis. So these can generally happen, for example, like let's say you have, like n qubits. So let's say it's an ion trap. Like, Professor Christopher Monroe has had at UFM. So let's say you have these qubits, so 1, 2, 3, 4, up till n. And then you are sort of doing operations on this by, say, like shining laser. So you want to do some sort of operation on this qubit. You apply, some laser on this to rotate the qubit, basically. And so while doing these kind of operations, one possible source of these coherent errors is, let's say, so you have the poly matrices, which I'll define shortly, but let's say you have, like, one of the poly matrices is the Z matrix. And let's say you're doing basically a Z rotation. So the actual operation you want to do is a Z rotation by some angle alpha. But what happens is, because you don't have like fully precise control over your operations, what happens is you do some extra angle theta. And so this theta is basically some over rotation angle, which was unintended. So this is one kind of scenario where coherent errors occur. So these occurs are coherent because they are basically unitary. So they're not a stochastic channel like stochastic errors. And as you keep doing these operations, these sort of over rotations can build up over the same axis. The angles just keep adding up if you don't fix them, and eventually things can break down. And so the scaling of these over rotations are pretty bad compared to stochastic errors, and that's why people care a lot about correcting coherent errors. So this is sort of one motivation to look at coherent errors. And so, for example, and that could also be, so this is one example where I said you are doing a particular operation and then you had this over rotation. But there could also be some sort of uniform magnetic field in the background. Which is basically causing all the qubits to rotate about an axis. And that can also be a source for coherent errors. In this case, your operation is basically something like e to the I theta z. So this is a rotation of angle, I guess we want, so this is a rotation by some angle theta z axis, and this is happening to all your qubits. So this is just the standard tensor product. So
I have a question. May I? This is Sasha speaking.
So
generally, one of the first models was the depolarizing channel where we had X, Y, X, Z, and Y Pauli matrices, and they were applied uniformly to every qubit. And a lot of research went into the analysis of that model, starting with the quantum constructions, channel capacity of the fully quantum channel, and so forth. Now you are saying you are applying a Z rotation to a qubit. So alpha is intended operation and theta is some noise?
Yes.
Is the noise random? Is theta random, or what is the model?
These can be correlated with the rotation you're trying to do. So this is basically an over rotation caused by imprecise control. So this is correlated with the operation you're trying to do.
But it cannot be fixed, right? For every qubit, it differs.
Yes. Yeah, so the theta will follow a distribution according to your model of your apparatus. So you can have a Gaussian distribution or something.
So like there is some distribution. It's a stochastic component that you add to the rotation, and that is the type of errors that you apply independently to the qubits, right?
Yeah. So the nature of the exact instance of what the value of theta is could follow some distribution. So in that case, it's stochastic. But overall, from a sort of the noise model perspective, these are called coherent because these are basically unitary operations. So the depolarizing channel that you mentioned is sort of a stochastic channel because it is sort of like the analog of your binary symmetric channel because with some probability it applies one of these Pauli matrices. So in that sense, it's stochastic. In this case, this rotation happens along with your gate, and that's why it's called coherent. But of course, if you want to be precise, you have to put a distribution on theta. But for now, but for today, we'll assume a simple model like this. And so let me again reiterate this. So in this sort of
Prakash, I had a question. Can you just go back to your, just scroll up a bit, please? So therefore, your theta is correlated to alpha, right? You're saying. Is it dependent on alpha, or it is dependent, right?
Yeah, it can be dependent. Let me. Yeah, I'm not sure if I think an experimentalist is probably a more appropriate person to answer this, but I think there could also be instances when the theta is just an extra rotation that gets applied accidentally, but it doesn't depend on how much you were rotating initially. I mean, it could be both ways, I think.
Thank you.
Yeah. Okay. So the coherent error for this talk, the coherent error model for this talk is quite simple, I should say, where we assume that each qubit is undergoing. So here I'm not actually assuming I'm doing any operation. I'm just saying one motivation is there's some sort of background magnetic field that's affecting all my qubits. And then it's causing each qubit to slowly rotate by some small angle theta about the z-axis. So that's going to be my model for this talk. Each qubit is rotated by theta about z-axis. So this can, for example, be due to some like Hamiltonian, which is like, sigma z on the first qubit. So sigma z basically on all qubits. And then, so this implies that, the actual unitary operation that gets applied is e to the I theta h, and which basically looks like e to the I theta sigma z1 plus dot dot zn, which basically gives the rotation I mentioned earlier, which is e to the I theta z turns around. So this, I'm just using sigma z and c interchangeably. So this is going to be my model. So people try to tackle coherent errors in different ways. So the approach in our in this talk, in our paper, is going to be the following. So design, so approach, and this is also kind of the main result. So design a stabilizer code such that this noise that we have, e to the theta sigma z tensor n, so each qubit being rotated by the z-axis by the same amount. So this theta is small, such that this preserves the code space but it acts trivially on my encoded information. So basically I have some sort of NKD quantum stabilizer code. I'm encoding K logical qubits in N physical qubits. This noise is acting on my N code qubits, and we'll design code such that it preserves the code space, which means it preserves the code, the subspace, and it acts trivially on my K logical qubits. So the noise is not a problem. So basically, this basically implies that the code is agnostic to the noise. And more formally, this is an example of what's called a decoherence-free subspace. So general DFSs are, there's a more general notion of a DFS, but this is one instance of a DFS. It's a subspace of the whole Hilbert space, which basically doesn't see the noise. Okay, so this is going to be, this is also we call it the approach, but this is also the main result. And the way we get there is in a few steps. So let me say steps or ingredients of the proof. So I just want to set things up at the high level before I get to the details. So basically, first we'll see something called as quadratic form diagonal gates. So these are some kind of quantum operations for which we have a very precise algebraic characterization. So so basically, what we'd be interested in here is how QFT gates act on polymatrices. So that's the first thing we'll see. So polymatrices form a basis for all square matrices of the appropriate size. And so if you characterize a unitary by how it acts on polys, you can basically characterize its action everywhere up to some global phase. So that's the logic for doing this. So first we do this QFT gates, and then we ask the question, when does a transversal, so I'll define transversal now. When does a transversal Z rotation fix the code space of a stabilizer code? So a transversal operations is precisely something that is that looks like this here. So a general transversal operation is where you have n qubits and the operation splits into a tensor product of n single qubit operations. Okay, so this is one instance of that because each qubit is going through a gate on itself. And basically this operation is not coupling two qubits. So that's what is called a transversal operation. So transversal means the unitary U basically splits into a tensor product of single qubit unitaries. And each thing can in general be different, but for our noise, each thing is going to be the same. Yeah, so here we, what we do is we apply the QFT result from the previous step to the code projector. So for poly matrices, the code projector you will see is basically a sum over some poly matrices. And we know how QFT gates act on each poly matrix. And then we just apply it by linearity on the code projector to arrive at necessary and sufficient conditions for when a transversal Z rotation fixes the code space. So when I say a transversal Z rotation, it includes this type of an operation. So this is a Z rotation by theta, and it's transversal because it's applied in, to each qubit separately. And so this is a special case of that. And then the third step would be to ask when does basically 2 happen. So this is 2. When does 2 happen for all angles theta? So this is for a particular Z rotation, for a particular angle to fix the code space. But then we'll ask the question of when it happens for all angles. And there's a simple argument that you can make that if a transversal Z rotation, like the form we have, fixes the code for all angles, then it has to act trivially on the code space. And then we are done. And so for this result, what we'll do is combine 1 and 2 with MacWilliams. And that will basically be the strategy we'll use. Okay, so any sort of high level questions? So hopefully this give you a big picture of what's to come in the talk. Any high level questions at this point?
At this level, it's clear.
Okay, thank you. Okay, so let me now get into the details. So I have to introduce some basics. I'll try to do that quickly. So, okay, so I'm going to quickly define poly matrices. So polys. So there are basically 4 poly matrices: I, X, Z, and Y, which is I times XZ. So these are the sort of 4 poly matrices. These are all unitary and Hermitian. And so if you take 2 poly matrices, 2 non-identity poly matrices, they anti-commute. So XZ is ZX, XY is minus XY, and ZY is minus YZ. Sorry. Okay, so these are, the single qubit poly matrices, and the single qubit poly group, also called as the Heisenberg group on a single qubit, is basically defined as being generated by I times the identity, or I to the, say, kappa times the identity and x, z, y, where this kappa is basically in Z4. So this is the full poly group. You're just basically including all kinds of products of these along with the scalars, the fourth roots of unity. And when you have n qubits, you basically have a tensor product. So the Heisenberg group on n qubits is basically the tensor product of all these single qubit matrices. Now there's a convenient sort of shorthand notation, binary notation for poly matrices. So I'll do that with an example. So for n qubits, you take two binary vectors A, B. So think of these as row vectors. So once you take them, the notation I'll use is EAB. Now, EAB is basically a Hermitian polymatrix. Let me take the example of n equals 3 and consider the polymatrix, say x, and then x on the first qubit, z on the second qubit, and say y on the third qubit. There is a tensor product in between. So I have 3 qubits. I'm doing x on one, z on the second, y on the third. Then my EAB notation will be, so I have A and B. Whenever I have an x being applied, the corresponding entry of A is 1. And then when z is applied, the corresponding entry of B is 1. And so the other becomes 0. And when I have a y, both are 1. You should have done this. So this is the shorthand for poly matrices, and it's super convenient. And this binary notation is basically what connects classical coding, or at least one important connection between classical coding and quantum error correction. So this EAB notation is something that I'll repeatedly use, and hopefully the notation is clear. So A is kind of the X component of the matrix, B is the Z component of the matrix, and their intersection gives Y. And that's all you need to do. Okay, and like I said, these poly matrices, these EABs, so you have 2 to the 2n possible tuples, AV, and these form a basis for all, so the EABs, if I take basically 1 over square root of 2 to the n EAB just for normalization, and take all possible binary vectors, this forms an orthonormal basis for all 2 to the n by 2 to the n matrices. Okay, so that's poly matrices in a nutshell. Now, the next thing we'll do is define what are called stabilizer groups. The stabilizer group S is basically a commutative subgroup of the n-qubit Heisenberg group that does not contain minus the identity. Okay. So we saw at the top that poly matrices commute or anti-commute. So for single qubit polys, any two non-identity poly matrices anti-commute. But when you get to more qubits, you can have situations where things commute. So for example, I had X, Z, and Y as my example at the top. Let me call this, say, E1. Okay, let's say this is A1, B1. So basically, this is A1 and this is B1. And you can take another example, say like Z tensor I tensor X. We call that EA2B2. And now you see that you can, because you know that the canonical product satisfies this property that A tensor B times C tensor D is AC tensor BD. And just by applying this property here, you can check that X and Z anti-commute. So there is one minus sign you pick up from this anti-commuting pair. Z and identity obviously commute, and then Y and X anti-commute again. So you have two minus ones that you pick, and so the two matrices together, so the whole matrices commute. And this is captured in the binary vector notation by what's called the symplectic inner product. So the symplectic inner product is defined as between two pairs, and it's defined as AD transpose plus BC transpose. Remember, all of these vectors are by row vectors. So this is an inner product, this is an inner product. So instead of the standard inner product, you basically flip the C and D before taking the inner product. And so this can also be written as AB 0 identity 0, and then C transpose T transpose. And this matrix basically flips C and D, and so you get the right inner product. And this matrix is usually called omega. Okay, so this is the symplectic inner product. And so this is equal to 0 if and only if, so the two matrices commute. So if EAB and ECD commute, it's 0, 1 if they anti-commute. And so this mapping, this what I call as the shorthand from this poly domain to this binary vector domain, it's a formal homomorphism because, so you're basically having this binary notation, and the main structure in the poly group is this commutativity or anti-commutativity, and that's also taken care of the mapping by the symplectic inner product. So this mapping from so Heisenberg while to this length 2n notation is a homomorphism. Okay, so that's poly matrices. And now, given this inner product, we can get back to stabilizer group. So stabilizer group is any commutative subgroup of the poly group, and it should not contain minus the identity. So for example, like you could form a stabilizer group using these two matrices as the generators. So you could just define the group as being generated by X tensor Z tensor Y and Z tensor I tensor X. So you have two generators and you have 3 qubits. So if you did a stabilizer group with EA1 B1 and EA2 B2 with these two as the generators, then this would basically give you an a 3,1 code, because you have so I haven't told you what a code is. So let's do it in the next page. So you can define a stabilizer group using these two. And now I'll get to what's called a stabilizer code. The stabilizer code is the subspace of the complex vector space of length 2 to the n that is fixed by S. So if I want to define the subspace, so let's say we have a stabilizer S, and let me denote the subspace as V of S, which is the code. So the code is defined as the set of all quantum states of length 2 to the n, such that each element of the stabilizer fixes the states pointwise. So it's the +1 eigenspace of a bunch of commuting matrices. So when you have a set of commuting matrices, we know from linear algebra that you can simultaneously diagonalize them. And if you simultaneously diagonalize them and take the intersection of the +1 eigenspaces of these matrices, then you get a code. And so going back to our example, so I define a code using X tensor Z tensor Y, and I think I did Z tensor I tensor X. And so this has basically two what you might call as parity checks, because you can take this to be G here, and then that gives you one parity check, because any code state has to be a +1 eigenstate of this. And then you get a second independent parity check from the second generator, and they should also fix the code space. So each parity check basically cuts down the space by half. And so this gives you, you have 3 qubits and you have 2 parity checks. So it gives you a 3,1. So any questions about the stabilizer code definition? Okay. And so, yeah, so these are, so you can now do the homomorphism, and then you can say that my parity check matrix or a generator or a binary generator matrix for my stabilizer is given by, A1, B1, A2, B2. So this is a 2 by 6 matrix. So this is length 3, this is length 3, and I have 2 generators. And so for an n, yeah, so I won't say too much. So this is under the homomorphism, and the row space of this matrix gives you the full stabilizer group. Question?
Row space, binary row space, right? F2 row
yes.
space.
Yeah.
And then we translate it back to the matrix, to the matrices, and that gives us the full set of stabilizers of the code.
Yes.
Mm-hmm. Very good.
Yes. So F2 row space of TS gives I'm being a little sloppy, but when I mean all of us, it means the binary representations of all elements of the stabilizer.
That's okay. That's understandable.
Yeah. Okay. Okay. So that's, I think, what I want to say about stabilizer codes. Let me maybe do a different example, because this will motivate so we are at the point where we can motivate our work. So let's take this example. I'm going to define a 6-2-2 code. Okay. And my stabilizers, so my G sub S in this case is going to be, so one stabilizer is all ones and all zeros. So hopefully it's clear that, so this means that the first generator is X on each qubit. So this is X tensor 6. And then here I have zeros. And then here I basically have 3 more, which are purely Z type. Okay, so let me maybe annotate on the top. So this is X on all qubits. That's the foot. Oh. So this is X on all qubits. This is Z1, Z2. So usually in quantum, we don't always carry these tensor products around because it's just annoying to keep writing them. And so people just put the matrix and then a subscript to say which qubit it's acting on. Sometimes people also drop the subscript. So they might just write this as Z, Z, I, or for short, I'll write it as Z1, Z2. And here we have Z3, Z4, this is Z5, Z6. But for a specific reason, what I'm going to do is each of these stabilizers here, when I define a stabilizer group, I can also add plus or minus 1 signs for each of them. So instead of just X tensor Z tensor Y, I could also put a minus sign in one of these. and it's an equivalent stabilizer code, but the code space will be different. So the properties won't change, like n and k won't change, but the actual code space will change. So in classically, we think of equivalent codes as, like if you permute the bits around, we call them equivalent codes because the distance properties and those things don't change. Similarly here, for an equivalent code, you can put signs in front of the stabilizer. So I'm going to put a minus sign for just the z-type ones and nothing for the x-type one. And these signs are actually crucial. So you'll see in the main result of our talk that one of the main conditions we have for these coherent errors to not disturb our code is how to pick these minus signs. Okay, so now here is our code. And here is the stabilizer matrix for the code. Now I can also write down the actual code state. So yeah, so I have these two logical qubits, and the sort of standard basis for the logical, the two qubits is 0 tensor 0, 0 tensor 1, 1 tensor 0, and 1 tensor 1. So these are just the standard basis vectors. So this will, if you can work this out. So this will just be the standard basis vectors. Okay, so this is the sort of standard basis for the two logical qubits. And so if I want to define the code, I can just define it by an encoding map. So just like we pick a generator matrix for a classical code, you could give the encoding map and define the code. So in this case, I won't go through why this is true, but you can basically check that the 0, 0 logical state, which is this thing, I'm just concatenating for simplicity of notation. So this, if you encode the corresponding 6-qubit code state, this is the encoding map. The corresponding 6-qubit code state for psi 0, 0, you can actually verify using this thing is this vector. And then you can similarly do for 0, 1, 1, 0, and 1, 1. You can look at our paper for the details. So you can look at this paper, which I said is one of the previous papers we wrote. So this example is discussed in more detail there. But what you'll see is all of these states, so psi 0, 0, psi 0, 1, psi 1, 0, psi 1, 1, all have a superposition of two basis vectors whose binary sort of index inside this angle brackets has weight 3. So it always has weight 3. For all of the 4 basis states, each of the 4 basis states, when you encode the actual code state will have a superposition of 2 things, each of which has having weight 3. And because of this, what happens is, let's say you want to do a transversal z rotation. So I'm going to pick up z rotation, which is like e to the I pi by 8z. So this is called as the T gate, and this is equivalent to this matrix. Okay, so we were looking at this code when we derived conditions for when T tensor n preserves the code. Okay, so you can immediately see by acting on the basis states that, so first of all, what you have to notice here is that with this definition of T, if you act on the 0 state, which is basically this column vector, you get back the 0 state. But if you act on the 1 state, you get e to the I pi over 4 times the 1 state. So this is the other basis vector. So just by matrix multiplication, you can see that 0 and 1 are eigenstates of this matrix, and these are the eigenvalues. Okay, now what happens if you apply T to every qubit in the code space? So you have 6 qubits. So this is actually a tensor product of 6 things. So if you apply T tensor 6 on this, you basically pick up an e to the I pi over 4 for each one. So you'll basically pick up e to the I 3 pi over 4 for the first thing. And then by linearity, you can also act on the other. And because this also only has 3 ones, you will pick the same face here. Hopefully that wasn't too hard to see. And because of this, what we have basically shown is that T tensor 6 acting on psi 0, 0 basically gives out e to the 3 I 3 pi over 4 psi 0, 0. And this global phase actually doesn't do anything in quantum, because in quantum, if you want to differentiate two states, you have to make a measurement. And these global phases cannot be detected, can't be detected by any measurement. And so this is equivalent to just the state you had. And therefore you see that doing this transversal thing fixed each of the basis states. So psi 0, 0, 0, 1, 1, 0, 1, 1, because they all have Hamming weight 3, and you pick up the same phase. And so it fixes each of your code states. So yeah. So it fixes each of your code states. And so it's not doing anything. It's trivial logically, because this was the 0, 0 logical state, and you're getting back the 0, 0 logical state. And this is true for, if you can try doing this for 0, 1, 1, 0, 1, 1, you see that it fixes the code space, but it doesn't do anything to your qubits. Therefore, this code is agnostic to this operation. So this transversal T basically doesn't disturb your code. And so if there was an error, so let's say our error model was this coherent error. Assume that the angle was this pi over 8, right? So if this happened to all qubits on this code, I mean, nothing happened basically. And this is a sort of motivation. And now you can see that this was, the argument I did was not at all dependent on this angle pi over 8. You can as well replace this by e to the I theta z tensor n, so tensor 6 in this case. And you can just apply this here. You will just pick up e to the minus I 3 theta or I 3 theta, whatever. So you just pick up some global phase and it fixes the code. So this code is, let me call resilient to these errors. And that's the key insight. So you didn't have to do any syndrome extraction, any error correction. If this thing happened, your code is still good. So is this key idea clear? Now this is basically the motivation. And now I'll quickly go through the steps of the proof in maybe half an hour or 35 minutes. I think this is a good point to ask questions about what's going on at a forum.
Well, the way you presented it, it was clear. I still wouldn't be able to say how would I construct this code in general, but
sure,
you'll say this a bit later.
Yes. Yeah. Okay. Yeah, I hope everyone else feels the same way. Now, let's take
just a question. This worked because all the elements of that code were right. All of them had weight 3. If they were of different weight, it wouldn't do that.
Yeah. So this is a sufficient condition for this to work. Let me put it that way.
Okay.
Yeah. Yeah. My intuition is that for all codes that this works, the basis state should be like this, but I don't have a proof for that. So let me not make a claim, but yeah.
Thanks.
Sure. So now, yeah, let's take a step back. So this is, so I gave you this explicit small example so that you can see everything in detail, but this is not, yeah.
When e to the, it becomes e to, the phase becomes e to the I pi, does it change, right? So
sorry?
If you add up all the phases and it becomes e to the I pi.
Oh, why are you adding the phases? So you're just having, so you're just doing linearity.
Suppose, I mean, I was just asking if it had like 4 ones in it. So some error flipped 2 ones in the code.
Okay.
So you'll add up to e to the I pi, right? So suppose there are 4 once in the code.
Okay.
So you said even if there are errors, it would not flip.
Yes.
So if I had added one more error in the 500 and it becomes to the I pi, right? Then
yes.
And that's now, would it flip the sign or something?
No, it doesn't do anything because, so my argument is just that, so you had this logical state. So let me call it in general x1, x2. So x1, x2 are binary. So I just did the 0, 0 example here. But any logical state, so you encode, so you have psi x1, x2. Now this goes through this whatever angle, so basically whatever angle you want, minus I theta z tensor 6. My argument is just that you get some global phase times the same state. And so, and if you unencode this, you will still get back x1, x2. So nothing happened to your logical states. I mean, nothing happened to your logical basis states when this acted. And by linearity, nothing happened because the encoding map is linear. Nothing happens to any of your code states because everything is a linear combination of these things. So you will run into problems only if it picks up a different phase for the first state and a different phase for the second state. Then there is a relative phase and that's non-trivial. But if you pick up a global phase, you're fine.
Okay.
Yeah. Okay. So yeah, so that's the basic idea. Now, clearly, I mean, if you want to design large codes or analyze large codes, this sort of state vector perspective is going to be super hard. Because if I had, say, 100 qubits, like I don't want to even like write a MATLAB code or something to actually write these things out and check them. So the state vector perspective is quite limited. And instead, we do all the analysis on this stabilizer matrix. So the same argument that I gave here explicitly on these states can be made using the stabilizer. And what that means is the following. So when you have a stabilizer code, which is generated by some plus or minus 1 signs, epsilon I, and say Ci di, and so you have say R generators. So this will be an n comma n minus R stabilizer code. So it's well known that, so this is a subspace, right? So this is a subspace. The code defined by the stabilizer is a subspace of the full Hilbert space. C2 to the n. So, and so because it's a subspace, there is a projector onto the subspace, and the projector onto the subspace V of S, which I'm going to call pi S, is you can verify this. So this is just identity plus epsilon I e C I d I over 2. So you take each generator you have, you do I plus the generator over 2 and take the products over all generators. And that is the projector onto the code subspace. I won't prove this, but with a little bit of thought, you can convince yourself that this is true. And so what happens is if you expand this, you get 1 to the R, and you basically get a sum over all epsilon EABs in the stabilizer group, and you'll just get epsilon EAB here. So this notation just means I'm summing over every element of the stabilizer group, and the argument of the sum is just the element. So this is the projector onto the code. And so necessary and sufficient condition for a unitary U to fix the code space. The fix meaning just preserve the code space. I'm not saying it has to act trivially on the encoded information. It just has to take code states to code states. So necessary sufficient condition for you to fix is that U basically commutes with your code projector. So you take the code projector, you conjugate it. So this is U conjugate transpose because U is unitary. This is also the inverse. So if it commutes with the code projector, it basically means that, so this is the same as writing U pi S equals pi S U. So yeah, if you act on the code states, you're preserving the code. And so what we do is, so instead of doing this sort of explicit state vector calculation, what you could do is using these generators, you could form the code projector, which will basically be a sum over polys. And then you would just want to verify that this conjugation gives you back the code projector. And so this is sort of the crucial thing we need. So now what I'm going to do is I'm going to set basically that U is e to the I theta z O tensor n, because that's the noise we care about. And I want the noise to first fix my code space. So I'm going to plug this in there, which means that if you expand the code projector here, what you need to know is this U, E, A, B, U dagger for all A, B. So this is the crucial information we need. So whenever we want to analyze if a unit tree preserves the code space, you need to know how it conjugates the poly matrices. And then if you have a formula for that, you can just plug it in back here and then hope to solve this equality, which will basically give you conditions on what ABs are allowed in the stabilizer generator or in the stabilizer group. And this is the approach we take. Is this sort of conceptually clear?
Yes.
Okay. Yeah, so this is what we do. So at the beginning, I quoted two papers. So one is this first paper, 1902-04022. So here we define something called as this quadratic form diagonal gates, which are basically gates of this form. So it's basically, so this is a symmetric matrix over Z2 to the L for some integer L. And the operation is basically defined as a diagonal operation where I'm indexing the rows, indexing each row by some vector B. So this is a 2 to the n by 2 to the n matrix. So I'm just indexing each row by a binary vector V. And this diagonal entry, so this is a diagonal matrix, and the diagonal entry indexed by V is given by Z to the V or V transpose mod 2 to the L, where Z is just a 2 to the Lth root of unity. So this is what we called as, so it's a diagonal gate. And so that's why diagonal, we call it quadratic form because the exponents form a quadratic form specified by the matrix R and the arguments being the row index. So these are the gates that we define. And so for U equals this tau R L, we characterized this conjugation. So I won't write down the formula here. It's not super important, but we basically gave a formula for this conjugation. So that's the first step. And a specific, and you can automatically see that a special case of this would be a matrix of this form, where theta takes some specific values. So you can basically set U equals tau R L using some matrix R such that the theta is now something like this. So it's a pi over, I mean, there is some details that I'm skipping, but let's say theta is of this form. So for these kind of thetas, using this definition, we were able to algebraically write down a formula for this conjugation. And then what we did, so this is this paper. And then in this follow-up paper, here what we did was we took this QFT formula, so applied QFT formula, by which I mean this formula. To the equation So we took an arbitrary stabilizer code. We asked, when does this conjugation preserve the code space for some specific R? And the specific R is corresponds to gates like this here, where theta is some angle like this. And now I'm going to write down necessary and sufficient conditions that we got out of this. So necessary and sufficient conditions for basically this, when tau RL is basically e to the I pi over 2 to the LC. Okay, the first condition we wrote down, do this properly. So the first condition we wrote down is the following. Okay, so this is the first condition. So let me parse this for you. So for any element in the stabilizer, which is of this general form, it has some sign, epsilon j, and the binary vectors denoting the stabilizer are aj and bj. So when you sum over this, this zj, so what is zj here? So zj is basically the subspace, so subgroup of pure Z-type stabilizers, which are of the form epsilon v E0v in S. So in S, first of all, this when we impose this condition, what we see is there has to be a lot of purely Z-type stabilizers. So there is no X component. So there are many Z-type stabilizers. So you take the subgroup of pure Z-type stabilizers that are supported on AJ. Okay. What I mean that that is this V, this binary vector V, which characterizes the Z stabilizer, is contained in AJ. So wherever V has a 1, AJ also has a 1. So the support of V is contained in the support of AJ. And that's this subgroup. So this is basically the binary subspace. So you wrote a subgroup, but it's basically a binary subspace of vectors V that correspond to pure Z-type stabilizers in the group, which are supported on AJ. And so when I sum over all those vectors, and this epsilon V is the sign of the Z stabilizer, and then I do I tangent 2 pi over 2 to the L, where L comes from my matrix definition. I raise to the Hamming weight of V. That should be the secant raised to the Hamming weight of the X component of my stabilizer. So it is this sort of trigonometric, complicated looking condition that we derived. And then there is a similar condition too, but I'm going to skip it in the interest of time, because for the talk, I'm only going to focus on this, just to give you a flavor of how this works. Any questions about this notation? So this is the sort of, so this is the condition. Now what we are interested in doing is, remember what we said is we assume this sort of coherent error, but for a general theta. And we wanted to ask when it preserves the code space for all theta. And then there is an argument that if it preserves the code space for all theta, for any core with distance at least 2, the logical action induced on the k logical qubits has to be trivial. Okay, so so we ask that question, and what we do here is we take this condition, this necessary and sufficient condition to preserve the code space, and we take these conditions and design codes such that, and derive conditions when this condition holds for all L. Because if it holds for all L, then by a two-adic expansion, you can basically express any other theta as a combination of these L's. And so if we satisfy this condition and the second condition, which I'm ignoring for now, for all L's, then every L, every transversal rotation preserves the code space and it has to act trivially. And so the main deal now is how MacWilliams interacts with this picture and how we are able to characterize when this condition holds for all L using MacWilliams. So that's what I'm getting at. So in the remaining time, I'm just going to do some MacWilliams. Okay. So MacWilliams. So the weight enumerator polynomial for any classical code C, which I'm going to denote by PC of x comma y, is well known to be a sum over all vectors in C, x to the m minus Hamming weight of v, y to the Hamming weight of v. So m, so this is a code of length L. So C is a code of length m. So this is the weight enumerator for a code. And the MacWilliams identities connect the weight enumerator of a code to the weight enumerator of the dual code. So this is a well-known, so this is the MacWilliams identity. And this is what we're going to use now. So the first lemma that I'm going to prove is that consider even code C. That means that every code word in the code C has even Hamming weight. Then remember, what is the condition we are interested in? We are interested in this condition. So now this code C that I'm talking about is basically the subspace ZJ. So you should think of the C as ZJ. And we know from some properties that this ZJ has to have only even weight vectors. I haven't told you why, but just from the stabilizer commutativity condition, you can deduce that ZJ has to have only even weight vectors. And so that's the code C I'm considering. So in this case, I guess, then this M is basically now this Hamming weight of AJ. So this code C, because we are supported on AJ, I'm puncturing all the other bits out. So wherever these vectors are 0 outside the support of AJ, I'm puncturing them. So this ZJ is a subspace of vectors of length AJ. And this Hamming weight of AJ is basically my this M here. So then this holds if and only if 2 to the L divides M minus twice the Hamming weight of W for all W belonging to C bulb. So this is the result I'm going to quickly prove. And we then generalize this. So you'll notice here that I'm ignoring these signs. So here in the general condition, I had these signs epsilon V. Now for simplicity, I'm assuming all these signs are +1 for this subspace, but then we generalize to -1 and so on. So this is, I'm ignoring the signs for the moment. So let me quickly do this proof. So we just rewrite this condition now. So I'm going to rewrite this condition by dividing by secant here. Okay, so what then happens is I get, so this is sine over cos, and this is 1 over cos. So when I multiply by the cos here, what happens is I get cos 2 pi over 2 to the L m minus Hamming weight of V I sine 2 by 2 to the L Hamming weight of V equals 1. And this, now you will realize that if you look at the weighted numerator polynomial, we had x to the m minus Hamming weight, y to the Hamming weight. And so I've just taken x and y to be, so this is now my x, this is now my y. And now, so this basically means I have PC of xy equals 1. And now I can apply MacWilliams. And so MacWilliams implies, now I get a sum over the dual code. And then I get, so remember the condition was we have the Bettian enumerator of the dual code with x plus y and x minus y. So here x plus y is basically e to the I 2 pi over 2 to the L raised to the m minus Hamming weight of w. And then x minus y e to the minus I 2 pi over 2 to the L Hamming weight of w equals 1. So this is just applying MacWilliams directly. And now what we can do is you can combine these two. And basically what you'll get is okay. And now here is the key thing. So we assumed that C was the even code. I haven't used this assumption yet. So because C is the even code, the dual of C must contain the all ones vector, because the all ones vector is orthogonal to every even vector. And so we use the fact that the all ones vector belongs to C per. And so I'm going to make a copy of this. So I'm going to do the same thing. So what this means is that for every vector that's in the code, the complement is also in the code. Because the all ones vector is in the dual, I can take any W and just add the all ones vector and the Hamming weight flips. So here I can basically make, so I'm making a copy. So in the copy, what I'm going to do is I'm going to do minus of m minus twice Hamming weight. So what I've basically done from here to there is I've taken, I've mapped Hamming weight of W to m minus Hamming weight of W. And then I get a copy and then I get a 2 there because I made a copy. And now you see that you can combine terms. So I have e to the I theta plus e to the minus I theta for the same theta. So it's cos theta. And I basically get a 2 cos theta. I get 2 cos 2 pi m minus twice the Hamming weight W over 2 to the L equals 2. So I basically now then have 1. And I'm summing over all the dual vectors, and I want this to be 1. So each term has to be 1. So this implies this is equal to 1 for all W, which is the same as saying 2 to the L divides m minus twice the Hamming weight of W. So was that proof okay? So this is basically how MacWilliams comes into the picture. We thought like it was quite wonderful because, I mean, initially this was a crazy looking condition. When we wrote this paper, we had no clue how to solve this. We did, so in this paper, we actually looked at the special case. We wrote this general condition, but we looked at the special case where L equals 3, in which case you get the T-gate example that I did for the 622 code. And for that code, we were able to, so this simplifies because tan pi by 4 is 1 and secant pi by 4 is root 2. So this simplifies super nicely. And for that case, we were able to exactly write down necessary and sufficient conditions, and it involved like self-dual codes. So, so this T example is particularly nice. And if you are a classical coding theorist, this has nice connections to self-dual codes. And we also proposed an open problem, which if we solve is a big deal for quantum computing. But this general case turned out to be non-trivial, but I mean, we work with Robert, right? So he immediately saw this MacWilliams trick. And so we can prove now this lemma. And now later in the paper, we also generalize this where we put these signs back. So we put these epsilon v's back. And then we get, so let me just write down the more general lemma. So lemma general is even code C. And then signs epsilon v non-trivial, meaning not everything is +1. And so now epsilon v is a character of the group, which means that half of the signs have to be -1. So exactly half of them are -1 and the rest half is +1. And when you have signs non-trivial, this condition 1 is satisfied if and only if 2 to the L divides M minus twice the Hamming weight of W for all W belonging to B perp minus C perp. So B is basically the set of all vectors in this code C such that the signs are +1. So you take, so B exactly has 1 dimension less than C. So because it's half of the vectors have epsilon v +1 and half of them have epsilon v -1. So B is the subspace that has epsilon v +1. And then this condition says that this divisibility holds for everything in B perp minus C perp. Whereas when all the signs were +1, we got the same condition, but for everything in C perp. So that's the difference. And now you can have a corollary. Okay, let's get back to our problem. So this is all MacWilliams, how it gets applied and how we connect to divisibility of codes. Now, what did we want to do? We wanted to satisfy this condition for all L, right? Now, for a given code, this Hamming weight is fixed. So, I mean, you're picking some X component of a stabilizer, and so this length is fixed. And if you let L diverge, 2 to the L is going to be larger than this Hamming weight at some point. And so when 2 to the L becomes larger than the Hamming weight, it's clear that in this condition, then the only thing that can happen when 2 to the L is larger than this is that this becomes 0. So when L is very big than 1, we see that Hamming weight of W is exactly M/2 for all W belonging to V perp and C perp. And this also says that when L diverges, the signs have to be non-trivial. Because if the signs were trivial, then our condition was that, this divisibility must hold for everything in C perp, but C perp includes the all 0 vector. So if this is 0 and 2 to the L is large, it can't divide M. So when L diverges, the signs have to be non-trivial. And then we get this condition here. And using this, we are also able to use Qubit polynomials. Implies that when this case is true, when this B perp minus C perp has all of the vectors have the same Hamming weight M/2, implies that C has basically M/2 weight 2 elements, weight 2 code words. And so whenever this L diverges, which is the case we are interested in, this B perp minus C perp, so remember C was the ZJ. So this needs to have all vectors of Hamming weight M/2. And using Qubit polynomials, we can easily you can quickly deduce, I'm not doing the proof, but you can deduce that this means that C, to start with, this even code, has to have many weight 2 code words. And in fact, it generalizes. It has to have code words of all weights, all even weights. So 0, 2, 4, 6, everything should exist. So this is the main corollary. And after this, what we do, since I don't have too much time, I'm going to intuitively do the main result. The main result is the following. So we have e to the I theta z tensor n fixes BFS for all theta, if and only if the following two things are true. So one, for each epsilon j, e, aj, bj belonging to S, so for any stabilizer element with a non-zero aj, the support of aj is a union. So I'm going to write something, but I'll explain what it is. I have to introduce something for this to make sense. Okay, so what does this mean? So I just showed you, I just mentioned this argument that this zj, which was C here, has to have a lot of weight 2 code words. So we define this graph gamma, whose vertices are n qubits. And then two vertices are joined by an edge. So here, let's say this is V1, V2. So this is vertex 1, vertex 2. So the two vertices are joined. So two qubits are joined if there is a Z stabilizer acting on the two qubits. So if plus or minus Z on this qubit, Z on this qubit, so this corresponds to these weight 2 code words. So if this belongs to the stabilizer, then those two vertices are connected in this graph. And these gamma k's here are basically the connected components of gamma. And you can see immediately that these connected components are fully connected. So they are complete graphs. So each of these gamma k, you have all possible edges between the nodes in the graph, which means that, so gamma k is a complete graph, which means the even parity check code which is of length gamma k, and so that's the standard even parity check code, which contains all code words of even weight. So this belongs to the stabilizers, meaning that there are many Z stabilizers, and for each of these connected components, you have an even parity check code's worth of Z stabilizers on those vertices. So what happens is you have these n qubits. So you have these n qubits, and these partition into these, if you want to call it like clumps. So this is gamma 1, this is gamma 2, this is gamma 3, all the way up to some gamma k. So each of these are the connected components of this graph, and these are your n qubits. And what I'm saying is each of these clumps has this even parity check code WK. So there is a W1 here, there's a W2 here, and so on until WK. So each of these connected components support an even parity check's worth of Z stabilizers. And then what I'm claiming here as the first condition, necessary and sufficient condition, is that each AJ must be a union of these clumps. So AJ must be, this notation means that AJ, when projected on that particular clump, so I said gamma k, right? So if you take gamma k, which is something in between, so there's more. So if you take the kth sort of connected component, you can argue that AJ has to be either the all ones vector or the all zeros vector. And whenever it's the all ones vector, so those are the qubits that are part of the support of AJ. And basically what we are saying is AJ has to be supported only on the connected components. It cannot have something outside these gammas. So AJ cannot be supported outside. So that's the first condition. And then the second condition is imposing signs on the weight 2 Z stabilizers. So we give a specific sign pattern for the weight 2 Z stabilizers. I won't go into those details, but all of this, so the necessity direction turns out to be easier, although I haven't done the proof. But the sufficiency direction, the sufficiency is repeated use of MacWilliams. The necessary direction turns out to be simpler, but for the sufficiency, the basic trick that I showed in the lemma that I proved, that is used in a more and more general setting in the sufficiency proof of this. So, but this is the main result. So whenever you have codes where the stabilizer satisfies this constraint that any X component is a union of the clumps, and then you impose the rights and the signs are stipulated in our main theorem. If these are satisfied, then all these transversal Z rotations fix the code space. And by a simple argument, it means that they act trivially on the encoded information, which means the code is resilient to this coherent noise that we considered. And we had some examples. So just in a minute, I'll just finish with this example. We have a more general family, but here is the 4x4 Shor code. So I have 16 qubits. And I'm going to draw my stabilizers on these qubits. And so the red boxes are basically X stabilizers generators. And then the blue boxes are Z's with, yeah, so this is Z with -1 sign. And then when I shade it, it's a Z with +1 signs. So this is, so going to the language of the theorem, so I have 4 clumps here. So the clumps are, so this, because I have a ZZ, ZZ, ZZ. So this corresponds to an even parity check code because I have this, so I have this 3 ZZs here. So I have 4 clumps. So that's, and those are my Z stabilizers, and then my X stabilizer, it's weight 8. So it is, so X on 1, 2, 3, 4, 5, 6, 7, 8 is 1 generator, and then 5 through 12, and then 9 through 16. And then we impose these minus signs on these unshaded ones, and we can show that it satisfies our theorem. And this is agnostic to e to the I theta. And so that's my example, and I'll stop there.
Very good. Excellent talk. In fact, a very nice work and clearly presented. Thank you very much.
Yeah, thank you. If anyone has maybe one or 2 questions, maybe I can answer.
I want to ask how restricted these conditions are like for general codes?
Yeah, so that's a great question. So one of the nice things that I didn't talk about, but we have in the work is, so I said this short code is an example of a family, but basically what we can do is think of our work as a black box. So you send in any NKD code. It doesn't have to be a CSS code. You send any NKD stabilizer code into our sort of coherent noise box, and we can give you at the output an M and K distance at least D code where M is even and which is agnostic to coherent noise. So you can basically feed in any code as an input, and with this, with the penalty of increasing the qubits M times, we can make it coherent to this noise. We can make this agnostic to this coherent noise.
In addition to keeping the distance, at least D.
Yes.
So that's an added property. It is not you're not replacing the earlier property, the stabilizer general error, quantum error correction property.
Yes. And so the distance can grow in, sometimes. And we also, if you look at the paper, we also have like scaling arguments for when the distance grows. And so there's a trade-off between, do you want to have rates being larger and larger or distance being larger and larger? And we have a discussion on that in the paper.
Thank you, that is excellent.
Sure.
Thanks again. I'll escape to class.
Okay.
Thank you very much. Very good.
Thank you.
Thank you. I came to catch the end of your talk, and I'll watch the immediate part tonight. Yeah?
Sure. Thank you so much for joining.
Thank you.
Let me know if you have any questions.
Sure, will do. Thank you.
Sure.